um, in our previous classes, we have considered fatigue under bending load as well as axial loads, and the common factor between them is that normal stresses are involved. We have not done any problem that considers fatigue under torsion, and the basic difference between these two is that torsion is a shear phenomenon. So we have shear stresses here, and we have mentioned in one of the earlier lectures that for the load factor Kc in equation 626, we are to use for torsion. If you have a torsion problem, we are to use a load factor of 0.59 for torsion problems. What it does, this Kc of 0.959, is it converts SE, endurance limit, to SSE, endurance limit in shear, because torsion is a shear phenomenon, so we have to convert our endurance limit to endurance limit in shear. And how it does this conversion is that if you recall, the von Mises, or the distortion energy theory, for ductile materials, we have done it in our yield criteria. For ductile materials, the shear strength, according to this distortion energy theory, is about 0.577 times the normal strength. This is the factor between, if you multiply the normal strength with 0.577, you get the shear strength. Now this 0.59 is an approximation. It's an approximation of the same thing. So this converts your SE to SSE. But there are some more adaptations too that are needed before we can apply this theory to torsion problems. And for that, we have to consider the fatigue diagram. Very familiar by now. It has the same shape as it had for bending and axial problems, only here now this value SSE gets plotted, not SE, because we're talking about shear now, so normal stresses are irrelevant here. Now this has to be joined to, instead of SUT in the case of normal loading, now we have to join it with SSU, and that is ultimate strength in shear. This S stands for shear. Now how do we get that one? That's easy. According to equation 654, SSU is simply equal to 0.67 of SU. Now this is an empirical relationship, and if we know the ultimate strength of the material, SUT, then you can just get this SSU by multiplying it with 0.67. So this, when you join these two now, this is your modified Goodman line for torsion problems. Similarly, if you have these two values, if you join them not with a straight line but with a parabola, the rest is the same. And talking about the Langer line in the diagrams that you are familiar with to date, it joined the SY on this axis to SY on this axis. And we have to now recall that this is now not a normal stress axis of amplitude component, but amplitude component of shear stress. And the strength, shear strength, so amplitude component of shear strength. Similarly, this axis is now for stress as well as strength, but they are now we are talking about shear stresses and shear strengths. This is the mid-range axis, and this mid-range stress axis, this is the alternating component, amplitude component axis. So now here also we would assume that it's reasonable to extend this whole thought, that instead of SY joining with SY, we have to join these two with the two quantities that we have to join are not SY but SSY. Similarly, and SSY is nothing but yield strength and shear, because SY is the yield strength of the material, but that is normal stress. If you convert it to the shear stress, and it's very easy to convert it again using the same one Mises criterion. SSY can easily be calculated by multiplying SY, the yield strength of the material, with 0.577. So this thing is valid here also. So if you join these two lines together with a straight line, this is the equivalent of the Langer line, or you can just say yield line. So this is how the strength part pans out. So the thinking is the same. You have the same fatigue diagram, but on the axis now you plot shear stresses and shear strengths, not normal stresses and normal strengths. So much for strength. What about stresses? Because we have to consider stresses also. So here we'll obviously, the stresses will be, this time you'll calculate tau A, tau M, not sigma and sigma M as you did previously. And once you have the stresses and the strengths, the rest is again very similar in approach. If you recall the modified Goodman criterion for your normal stress case, it was something like sigma A over SE plus sigma M over SUT is equal to 1 over NF. This was your equation for the modified Goodman line design equation. Now just replace the shear equivalents of all these quantities, the shear counterparts. Simply this is all you do. So in other words, NF turns out to be 1 over this is your expression for the fatigue factor of safety. Of course, this is for the modified Goodman criterion, but you can have similar expressions for Gerber, ASME, elliptic, etc. There's nothing difficult about that. Now, at the end, even if it's a question of fatigue, it's good practice to check yield. And if you recall the Langer equation, the original Langer equation, that was sigma A plus sigma M is equal to SY over ny. This is the yield factor of safety. And you just replace now because we are dealing with TOS now. And here in place of sy, you'll have sy, yield strength in shear, ny. Or in other words, ny is equal to ssy over t tau a plus tau m. This is your yield factor of safety. And recall that SSY is obtained by the von Mises criterion using the number 0.577. You multiply it by the yield strength and you'll get this yield strength in shear. So we'll demonstrate these adaptations for torsion problems by solving a numerical problem.